Hi, everybody. I'm Pranay. A couple of years ago, but I'm gonna ride the mustache gravy train. um, yeah, and I'm super excited to present the Ethereum Wayback Machine here, which is a solution and a modular EVM long-term data availability and a data read scalability solution. And this talk is basically divided into three sections. The first section, I'm going to talk about a bit about myself and my history in blockchain data. Then I'm going to talk about the long-term data availability problem in blockchains, talk a bit about Bitcoin and Ethereum. Then we talk about primarily the meat of the presentation, which is the protocol, the different kinds of actors in the protocol, the components of the protocol, how we achieve this, a bit in numbers of how the protocol has been adopted, ending it with the mission and the future work. So let's get started. Right. So about 5 years ago, I built a tool called fee estimation using neural networks. And the idea of this tool was to estimate gas fees on Ethereum. This is proof of work Ethereum, using historical signals, which are basically mined transactions. Along with the mined transactions, I also looked at miner signals like the number of miners, the hashing rate, the total number of unconfirmed transactions in the mempool to get an overall picture as to what was basically contributing to the increase or decrease in gas fees. This enabled me to build a complete historical representation of what gas looks like, and we created these neural networks in three different categories: slow, medium, and fast. There was great adoption of the API, primarily because we were able to estimate gas fees 30% cheaper than ETH Gas Station, which was a popular gas service at the time. And we got up to 345 invocations a second, which is almost 30 million calls a day. From this, I learned there's deep historical information and insights that can be gathered from long-term data, right? And the way we look at it and the kind of tools we use will determine that result. If you peel into the history of blockchains and look at Bitcoin in particular, the very first Coinbase transaction, which is the reward transaction, has a kind of message embedded in it by the original author. Many of you must know about this, but basically it's a hex script signature, which if you decode points to this headline on the Times. What the author is trying to say is basically how the chancellor bailed out all the responsible banks for the financial crisis at the cost of taxpayer money. So we have this kind of information available on-chain for all of history, but who's really looking at it, right? And if you look at Ethereum in the past, there are signals in the protocol with respect to the changes that have been made over time that can be gathered as well. So in this case, I just plotted 4 timelines in the history of Ethereum since about 2014, and I chose the ones that were responsible for the changes in state. I think Daniel mentioned how rights are preferred in blockchains, and this is something I saw again where the different opcodes that relate to being able to read from the state of the chain, like sload and xcode hash and delegate call, the gas amounts were increased anywhere from 20 gas to over 2,600 gas. So it's been harder and harder to read state. And the reason this happens is because sync efficiency of the nodes is triggered as a result of reading through these gas opcodes. And there was an attack in 2016 called the Shanghai attack, which is a denial of service attack, where the attacker basically accessed multiple storage accounts, and as a result, brought down the sync of those transactions to 80 seconds compared to like a few milliseconds that it takes to like sync a transaction. These kind of insights are gathered from looking at this kind of historical information which is embedded. So, and in the future, the scaling for Ethereum is going to be focused on removing state history, further removing the long-term data that many applications might need. And in this scenario, we have the surge in which you are basically providing a way for rollups to scale on Ethereum by a sidecar data blob, which we call shard blob transactions, which is EIP 4844. And here the idea is that all rollups can post cheap data here, but this data is kept only for a short time, maybe for a few months, and then it's erased from history. So who's going to keep this? And if we need to access this, where are we going to go, right? Are we going to go to centralized authorities, or are we going to go to decentralized infrastructure? Similarly, in the purge, after a certain amount of time, there's going to be an expiry of all the history, and legacy transactions wouldn't be available. So we do need, for applications like taxation, regulatory compliance, machine learning on transaction data, which enables building investment strategies and other such insights, access to this information in a verifiable, trustless manner. And how can we achieve that? I introduced to you the EWM, which is a universal, modular, EVM long-term data availability and read scalability protocol. And the way in which we achieve this is through two chains. Here, the stake chain, proof chain, an event sequencer that is able to relay messages across these two chains, a decentralized store where we are storing all the data artifacts for the long-term data sharded by blocks. We'll talk a bit more about what these data artifacts are. We currently use IPFS for this. A bunch of protocol actors, delegators, validators, block specimen producers, block result producers, etc. But the core idea is that using this protocol design, you're able to create a layer where you have the pointers to the data artifacts, where anyone can read the pointers and get all the data artifacts and create a data warehouse on their own if they had to, thereby recreating the entire history of the chain right from the data pointers, right? And so the entire blockchain history can be read off of what we call the proof chain. So let's get into the individual components a bit. The block specimen producer is the primary export specification of block data. And within this export specification, what we do is we extract the state history, what we call the state specimen, which is a set of all the accounts, the storage slots, the balances, the code hash, everything that is happening at the time of the sync of a node, we extract and present in this binary format, right? And the block specimen producer, as a validator, stakes on the stake chain, where he commits to doing this work. He creates a proof transaction, and he relays that proof transaction on to the proof chain. Now, the proof chain is not an EVM chain, but is a BFT Tendermint consensus Comet BFT chain, where we can have different kinds of storage models. One of the storage models that we are using is the account-based one, and the other one is a UTXO one. And here, the IPFS is basically storing the result of the computed data artifact as a result of that extraction. So the block specimen as a specification is extracted, posted on IPFS, and a proof which carries the CID, which is the content identifier to that block artifact, is posted in the proof transaction. Thereby, we then aggregate all the proof transactions across multiple validators who are doing this work and develop a consensus on who did the computation correctly. In the next step of the process, we take this raw data artifact, which is the block specimen, and condense it by re-executing it in a transition tool we call the EVM transition tool. And the core idea is that you can do EVM computations outside of the execution layer, which is, say, an RPC node. Right, so the block result is then a one-to-one representation of a JSON RPC-like response that you would get from an RPC node. And now we have individual block results computed outside of a node that can be reindexed at any arbitrary block number by any data warehouse producer for any chain. And so you can have a query node operator that is ingesting these data artifacts, creating the history from where they want to, and producing proofs of those queries that they're serving to applications. So inherently, we come up with this design where you have multiple validators producing work in terms of computations, off-chain computations, making a result of the off-chain computation as a result of an on-chain transaction, collecting or aggregating all the proofs from those on-chain transactions, and creating a history of verified blockchain data in the form of sharded blocks, which we call block specimens, right? So this is the overall protocol diagram. And we have seen a great adoption in this protocol over the last few years from when we released. we have released both the block specimen producer as well as the block result producer, which we call the refiner. If you have questions about how we aggregate these proofs, we can go into it. But currently, we are using a naive model or an optimistic model where we are evaluating all the proofs that have been sent by these validators, and we check for fraud proofs. And the cumulative proofs have grown to quite an extent over time, which points to the decentralization and the number of increasing protocol actors. Further, because we have to use incentivization mechanisms, we use the CQT token as a staking token for the commitments to the work that the validators would like to do. And the rewards accumulated as a result have been increasing over time. So more and more validators are coming into the network and producing these proofs, which can then be used to recreate the entire history of the chain. Finally, I'd like to talk a bit about what the future work of the EWM entails, which is node development. We are going to migrate staking back to Ethereum. Currently, we are all deployed on Moonbeam. We're going to add additional storage services besides IPFS, where we can store these artifacts. Decentralization of the event sequencer is a major aspect of scaling. Further, we're going to use KZG commitments for the blob transactions that are happening on the beacon layer, expand the specification to support other chains like Polygon and Arbitrum, and basically integrate the BSP fork into clients like Nethermind and Besu. And finally, the query fees that is generated from the query node operator is going to feed back into the supply chain of the data artifacts that's being produced by various validators. And this enables us to create a compute and storage-based revenue distribution across operators. So finally, I'd like to leave you with the mission statement, which is the core mission is to achieve complete EVM state data retrievability and reexecutability in a trustless manner with efficient open source tooling. Thank you.